Hi, I am Dr. Samir bin Osman, and in this video we're going to talk about the principles of chemistry. So chemistry is the studies of the properties of atoms and the molecules that they form, as well as their interactions. So where does the chemistry happen? Basically, the short answer is it happens all in the electromagnetic force that we talked about in the principles of physics. So the electromagnetic force binds electrons to atomic nuclei, thereby forming atoms that interact using their electrons to form molecules that also interact with each other. Therefore, all chemistry happens within the electromagnetic force. It determines the properties of atoms and molecules, as well as how these interact to form other molecules. You can see here a depiction of a nucleus of an atom formed with positive protons and neutral neutrons, around which we have negatively charged electrons. Of course, the size is exaggerated, and the distance is not exaggerated at all. So, like, the atoms would be much bigger in terms of distance between the nucleus and the electrons, and there will be a lot of space between them, and also the size of the electron would be much smaller than the size of the protons and neutrons, just to give a kind of a reality check here. And so the number of electrons in an atom determines how they arrange in space, and therefore it's going to dictate their chemical properties. Since electrons are proportional to protons, because they have to balance the charge, and because neutrons don't have a charge, and since the number of protons does not change, contrary to neutrons that can change, the properties of an atom are then defined by their number of protons. Now, the mass of an atom is defined by the sum of its protons and neutrons, just because the electrons are basically negligibly light. So 99% of the mass is within the nucleus. Now, some atoms occur within in nature with a different number of neutrons, i.e. more neutrons than protons. They occur naturally, and they're called isotopes. And those will tend to try to lose those extra neutrons to get to equilibrium. Like we said, the general principle, the overarching principle in the universe is to try to get to equilibrium and maintain equilibrium. So those atoms will try to lose their neutrons through the weak force, and thus emit beta radiation along the way. And that actually, just as a side note, this radiation they make generates the heat in the earth that causes tectonics, which was essential to the establishment of light. And we're going to talk about that when we talk about geology. So let's talk about like how these atoms organize and the conformation that they take. So because electrons behave according to quantum mechanics, they don't move in a linear way, but they have probabilities of presence, which are, like we said in physics, high in some places and very low but not null in other places. So these probabilities of presence can only allow the presence of one atom at one spot at a time, which is called the Pauli exclusion principle. Therefore, additional electrons that are around the nuclei have to occupy farther away regions with different probabilities of presence. And these form like a 3D probability of presence shape, let's call it. And we call that orbital. You can see here in purple, those are electronic orbitals that the electrons take, starting with the lowest energy one, which is a sphere, and going up, basically in energy. As the electrons, like other subatomic particles, they want to minimize their energy. Like we said, it's a general overarching principle. They will try then to occupy the orbitals that are close to the nucleus first, the low energy orbitals. And then when they can't, they will have to occupy the next ones until the electrons occupy the outer orbital, which is called the valence orbital, and which is what all the chemical interactions with other atoms is going to occur. The lowest energy orbital, as you can see here, is a sphere. But higher orbitals, they have to adopt different shapes to avoid conflicting with the other orbitals because of the Pauli exclusion principle. And so the shape and number of these orbitals in each atom is going to determine the shape of the valence orbital of the last one, and that's going to dictate the geometries that are allowed by which those electrons can interact with other atoms, i.e. they will form, let's say, cubes or triangles or like tetrahedrons, etc. And that's actually very important because that's going to determine the properties of the resulting molecules. And you can see here, for example, the 3D representation of the orbitals in a molecule of water. And you can see that it's, what do you call it, like a trihedron, or it's basically like 3 triangles. And that's actually very important for its shape, and we're going to see why it's important a little bit later. So these atoms and elements, they accept a specific number of electrons before they have to jump to a higher energy orbital, like we said, until they reach the valence orbital. Now, what we have noticed is that atoms of different masses, i.e. different number of protons and neutrons, but with similar percentage of their valence, that is filled or not filled, they tend to have the similar properties, i.e. Let's say that an atom only needs two electrons to fill its orbital valence. Whether it's lighter or shorter, they will have still similar properties. And so there is kind of a periodicity in the properties of atoms. And that's how they were grouped into what we call the periodic table. And this is how it's organized. So you have the elements with the most, the completely filled valence orbitals. They're basically very stable. And those atoms, therefore, do not seek to interact with other atoms because they're like completely stable. And they're non-reactive. And they're grouped in a family called noble gases, as you can see highlighted here. Now, some other groups of atoms, they will lack a very small number of atoms to complete their valence orbital, and therefore highly seek to gain that small number of atoms to fill it. Those elements are therefore fairly reactive and are grouped into alkali metals and alkaline earth metals, as you can see here. These are the two groups. Now, on the contrary, elements that only have a minority of their available valence spots occupied highly seek to actually give away those lone electrons and are grouped into halogens, and they're highly reactive with the other groups which basically seek to do the opposite. Now, groups that fall between all these two, they have little incentive to either gain or lose electrons and are therefore less reactive, and rather tend to share their electrons between their valences among similar elements. And we're going to talk about the links that they form, or the bonds that they form. So how do atoms and molecules bond then? So the atoms always seek to minimize energy inside them, but also between them. Hence, when they get close enough and with the right amount of energy, etc., those atoms will form what we call intramolecular bonds, i.e. bonds inside the molecules, and they will form then molecules. And so the molecules are basically atoms having intramolecular bonds. Those resulting molecules will have a lower overall energies than the separate atoms. And that's why the reason they want to combine into molecules, obviously when the conditions are right. For the same reason, molecules minimize energy between them through what we call intermolecular bonding. So a molecule and a molecule will seek also to do the same thing that atoms did, but the links between them, the bonding between them, is much weaker than the bond between the atoms. Also, molecules will exchange atoms with other molecules, forming new molecules in what we call the chemical reactions, and we're going to talk about them in the later slides. Now let's talk about the intramolecular bonds. So elements that are in less reactive groups, they will tend to share their valence electrons, like we said, and basically they will form molecules with elements that are similar, have similar propensity to share, and they form what we call covalent bonds. Covalent means like everyone shares an electron, and these are actually the strongest and most stable bonds. And you can see here they form basically like the electrons, they will form a halo around the two atoms, it's like enveloping both of them, and that's why they're strong. Now on the other side, the elements that are less reactive in less reactive groups, or in more reactive groups, they will tend to share their valence. The elements that are more reactive, they will prefer to give or accept a few electrons to the opposite reactive group, to the opposite atom. And thereby they will make bonds that are called ionic bonds that are weaker than the covalent bonds, but they have an additional kind of characteristic. As we said, the chemistry happens in the electromagnetic force. And so whenever bonds form where there is kind of a penchant on positive on one side and a negative on the other side, like for example this molecule of salt, table salt, NaCl, and you can see that Cl gains that electron, and so from Na, and so it gets more negative because the electrons are negative, and Na, by losing electrons, becomes more positive. And so because of that, the molecules will behave like teeny magnets by forming poles. You have like, a positive and a negative pole. And as such, ionic bonds are more polar than covalent bonds. And and this is actually a very important property. We're going to talk about it a little bit later on. Depending on their direction, those polar bonds can amplify or cancel each other, because we said the electromagnetic force is unidirectional. It's very sensitive to direction. And that's why the geometries allowed by the valence orbitals in their atoms are important, the 3D shapes that we talked about just earlier. Therefore, the overall geometry, i.e. shape, and the polarity of a molecule has a profound impact on its characteristics. So for example, non-polar molecules, they will dissolve in non-polar solvents, i.e. oils. For example, here you have gasoline, which is non-polar, and dissolve means basically just like insert themselves between them, So when dissolved, polar molecules will exhibit an electromagnetic charge and allow the flow of electrons, and therefore conduct electricity, while non-polar molecules don't. And so this electrical conductivity is actually essential for most biological processes that rely on transmitting electrons and transmitting electrical force, and therefore explains why water, as you can see here, is the solvent, universal solvent for all biological systems. Now, some molecules will combine both a polar and non-polar region. As you can see here, that the tail is basically a non-polar lipid-seeking, lipid-dissolving region, and the head is made of a phosphate, and it's polar, i.e. it's dissolvable in water. And so these molecules, they will be able to dissolve in both polar liquids such as water and non-polar liquids such as oils. And so these called surfactants. And one such molecule that everyone knows is soaps. Soaps, detergents, emulsifiers in cooking technology, all of them are surfactants. Now let's talk about the bonds. Now we talked about the bonds between atoms. Now let's talk about the bonds between the molecules. So like we said, the electron clouds that's going to surround the plus or minus extremities of the molecules, they will also act like little magnets. And those magnets will bring them closer, forming what we call intermolecular bonds. At low temperatures, those molecules will have less kinetic energy, i.e. heat, and tend to then cluster in tight configurations, forming what we call solids. As temperatures increase, their increased motion forces them into looser arrangement, forming liquids, and then gases, actually. I just want to point your attention towards kind of a special case of intermolecular bonds, which is the hydrogen bonds. Why is it so important to talk about those? So hydrogens, they tend to get attracted to oxygens and nitrogens from other molecules, forming what we call hydrogen bonds. And especially in the case of water, which is H2O, hydrogen bonds are so numerous because basically it's basically H and O, and H likes to have those bonds with O, those hydrogen bonds. And so those hydrogen bonds are so numerous that they give water its unique properties, such as what we call cohesion, which is the ability to stick to itself, and adhesion, which is the ability to stick to other polar molecules, which makes it the dominant solvent on Earth, as well as other characteristics such as high specific heat, which is the high capacity to retain heat, which is actually 5 times that of rocks. And that allows also oceans to regulate Earth's temperature. It also allows them to circulate heat and nutrients between its regions and through oceans, through ocean currents, And ocean currents, we're going to talk about them in geography, but they're actually generated by the dissolved salt ions from rocks, and which causes fresh water from the glacier to pull salty water, thereby generating those currents. And so you see how these characteristics of water actually they make life possible on Earth. And that's kind of the importance of hydrogen bonds. The other importance of hydrogen bonds is that they're actually key to forming the essential building blocks of life. So proteins and DNA rely on hydrogen bonds, as well as actually in all pharmacology, the drugs that interact with proteins and DNA, mostly with proteins, they actually almost entirely interact with them using hydrogen bonds. So you can see the importance of this specific intramolecular bond. So with that, now that we talked how they bond, so if we put many molecules together, what happens? Well, we got chemical reactions. So let's talk about those a little bit and the principles that govern them. So under the right conditions of heat and pressure and pH, etc., molecules will exchange either groups of atoms or a single atom or even hydrogen protons, i.e. H+, basically the hydrogen without the electron, or just electrons with other molecules. And those that exchange, we call them the reactants. And they will form new molecules, and those new molecules, we call them the products. And so these reactions can be either complete reactions, whereby all the reactants turn into products and then the reaction stops, or most commonly, they will be what we call equilibrium reactions, where actually the reaction happens in the two directions, like forward and reverse. And so the products also reverse transform back into reactants at the same time. And regarding those, the speed of these equilibrium reactions in one direction or the other is dictated by the initial conditions, like we said, heat, pH, concentration, etc., and therefore can be nudged one way or another by changing these conditions, i.e. adding more reactants, adding more heat, adding more pressure, etc., depending on the reaction. Now, some molecules that do not participate in a reaction can help either activate that reaction or actually significantly speed it up in one direction, and they're called catalysts. And especially in biology, this function is done by specific proteins called enzymes that are basically the ultimate catalyst, and they're essentials for actually most reactions in biology and most reactions in our body and in our life. I just want to conclude by giving some examples of notable chemical reactions, some that are important, some that are kind of just interesting. So the ones that are important include oxidation, which is the reaction of oxygen with many components of life in biology, including kind of respiration that enables us to extract energy and to live, but also oxidation that happens in metals. We have also like another important reaction, which is photosynthesis, which is what the reaction that the plants use to make sugars from O2 and CO2 in the atmosphere. We have also the reaction of respiration, which is making energy storage molecules called ATP from sugars and oxygen. And then the interesting one that I want to mention here, or I guess the tasty one, is the Maillard reaction. And the Maillard reaction is basically the reaction that makes sugars and proteins interact and modify under heat, making tasty products. And basically that's what it gives cooked products their taste. So when you put a steak on a grill, the browning reaction, that's the Maillard reaction that's going to give it its taste. So on that, I guess, tasty note, I'm going to conclude this video on the principles of chemistry. I would love your comments, and thank you for your attention.